Hi, this is a honors section for chapter 14. Chapter 14 is a discussion about the thermodynamics. And during the thermodynamics, especially it's going through one process to another, we have several different spatial processes that we are interested. Then the things that we most interested is the what will be the work done by these processes. So let's look at the work and how do we define the work? That is the topic we're going to discuss in this video. So the work, the definition of the work is the force times displacement. So if you apply a force to an object and a move with certain distance, the change of the distance, the displacement, will give us the amount of the work. So to write this in a mathematical equation, we can write this in terms of this way. The dW meaning how much work that you actually applied. And that's equal to the force F times dx. If x is the direction, they will apply the force with. And then the work done by the force along the x direction will be F times dx. Now we're going to change a little bit to see what happens if this work is done by the gas. Well, when we can introduce the equation of pressure. So remember how we define pressure. Pressure is equal to force divided by area. So if we divide the whole thing with the area and we multiply the area back such that I didn't change anything, then I multiply with the dx. Then the equation of the work become F over A times A dx. Now, what is F over A? That's force divided by area. That is actually the pressure. What about A dx? The A meaning the cross-section area, and the dx is its movement along the x direction. And if you have an area times the depth, that simply represent the volume. And because you are looking at the change of the distance, that is similar to the change of the volume. So work for gas, that work is simply equal to P times dV. Now we can write this if we really want to find out how much work done by the gas, then we really need to take the integration. So we take integration on both sides. Then you're looking at how much work that you did for this. And this will be the VI of the VF. And this is the definition of finding the work. So this one, if you do the integration, is simply just W. So work due to the thermodynamics process for an ideal gas is equal to this. Now let's look at the following pictures to show you why and how do you think of this and related to the work. If you have a piston, like the picture that we show and here, and if initially there's a pressure inside of the gas, and we have this gas with a pressure, and it's going to expand. Which means the inside pressure is larger than the outside pressure, so it will expand. If it expands, meaning there's a force inside of the gas is pushing to the piston. And that force is related to the pressure, and that force is this much. That simply is equal to the pressure times A. And we know the work is the force times the displacement. If this piston move along the direction of x with dx, and then you can see the work is simply equal to this equation, which is the equation that we just derived. And therefore, this is the equation that we just gave you, and the work is simply just dp times dv, and that is the change of the volume from the initial v sub I to v sub f, where v sub I in this case represent this much of the volume, and this is our v sub I. And the v sub f represent the volume of this much, because it expand, and therefore this is your v sub f. We can write this in another way if you make a graph. And this graph is a graph that we use a lot in the thermodynamics. This is what we call the PV graph, a pressure versus volume graph. For any of the thermodynamics process, we describe this process in terms of the state variables. The pressure, the volume, they are state variables. When you have a different pressure, different volume, that represent different state. Another state variable is the temperature. But normally we will use the x, y as the pressure and volume to describe this kind of process. Let's look at some of the basic process. The first process that you look at here on the left is what we call the isobaric. When you have an isobaric, meaning the pressure is a constant. So when the pressure is constant, it doesn't change during this process. This is what we call the isobaric. If when you are doing a thermodynamics process and you keep the pressure to be constant, and you move from the state A to the state B, and that means you don't change the pressure, but you change the volume. The pressure keep a constant, and the volume is going to increase. If that is the case, then we look at the work done by the gas. What that tells you is we change from some initial volume to a final volume, and our pressure is a constant, and we have to integrate with respect to the volume. Now this is a constant. If you do the equation integrate with a constant, you can take the constant out. And you take the integration of dv, simply give you a v and integrate from v sub I to v sub f. And therefore, this is simply just the p times v sub f minus v sub I. And we can also write this change of the volume to be the delta v. Notice in this case, we're doing an expansion because the final volume is larger than the initial volume. So your delta v is actually a positive number, which means work done by the gas during the expansion is a positive work. Let's look at another situation. This one is more interested than the isobaric. Isobaric simply means the pressure is a constant. What about if we do some kind of expansion, but we don't keep the pressure to be constant? Instead, we use temperature to be a constant. If you keep the temperature to be constant, this is what we call the isothermal process, which means temperature is a constant. Then how do we find the work done by this process? Again, when you look at the work done by this process, you are looking at the area under the curve. For the isobaric, you can see the area is simply just the P times change of V, and that's exactly what we derive from the equation. So the equation simply represents how we integrate the area. Now, this rectangular is easy to calculate. However, if you look at the isothermal process, how do you find the area under a curve? And how do we represent this curve? Well, if this is an ideal gas, for the ideal gas that you know, the ideal gas has an ideal gas equation. That is the PV equal to mRT. And this number of the mole, R is simply just a constant. So if temperature to be a constant, then we can say this is simply just equal to the V. If temperature is a constant, I can represent the pressure to be the V m RT. Now, m times r times t, they are all constant, so you can treat all those things just simply just one, a big constant. Let me just say this is a k, and divide by the v. So I can represent the ideal gas, and how the pressure is going to change is simply just based on the v. This is what this equation tells us. The thing we are interested is, if this is a process, then how do we find the work done by the gas? Well, when you look at the work done by the gas, you use our definition of the work done by the gas as the integration of initial volume to the final volume, and you use the P times the V. But this time, the P is no longer a constant. And what happened is the pressure actually depends on the volume, and how they depends on the volume is equal to this over here. So I can write this as this way. then we are integrate the K over V dV, where K is simply just constant. K is equal to MRT. Now, MRT can be taken out from here, so you can say this is MRT outside, and what we really integrate with is dV over V. Now, this dV over V, if you do the integration, is going to be a natural log. So this is one of the important things that you learn in the calculus. This is simply MRT times natural log of a V, and you integrate from VI to VF. So we can write this as MRT, the natural log VF minus natural log of a VI. Well, the natural log has a property. If you have the natural log of A minus natural log of B, that is also equal to natural log VF over VI. So I can also rewrite this as MRT and the natural log VF over VI. So this one simply just gives us, if you have a gas and you do the work in this isothermal process, this work done by the gas is equal to MRT times natural log of a final velocity, final volume divided by the initial volume. And that's how we did this from the thermodynamics and from the calculus. Okay, let's do one example over here to show you how we can use this equation to help us solve a thermodynamics problem. The problem over here, we're looking at one more of the sample of an ideal gas. By the way, the PV equal to MRT only valid for the ideal gas. If it's not ideal gas, you cannot use that equation to get the equation of the work done by the gas, as we show you a moment ago. So ideal gas. So that's nice that because we already have the equation, and we kept at a 0 degrees Celsius during an expansion from 3 liter to 10 liter. Some of the things they have to be careful when you do this kind of calculation is not only that you need to know what equation that you should use, you also need to know about the unit as well. Okay, so since we already tell you in this situation what equation that you should use is this equation. Right? Based on our derivation, the work done by the ideal gas during the isothermal process is equal to MRT times natural log of VF over VI. And then we have all the information provided from this problem. They tell you this is a 1 more. And what is R equal to? R is a constant. And the unit for this R is joule per mole and K. And what is K? Well, K is the Kelvin temperature unit. So that means when you do the calculation, the T, the temperature, cannot be in Celsius. It has to be in Kelvin. And 0 degrees Celsius is simply equal to 273 Kelvin. And then you multiply with the natural log of the volume ratio. The final volume is 10 liter. Initial volume is 3 liter. Now, as long as you use the same unit for the volume, then you don't need to do any of the conversion because liter and liter, they will cancel out. So if you use the meter cube, they will cancel out as well. All right, so then if you put all these numbers, use calculator, then you can find out the result of this is 2.7 times 10 to the third joule. And joule is the unit for the work. Okay, so if you wanted to expand this problem, let's say, what about we wanted to know how much energy is transferred by heat occurred during the surroundings in this process. So let me write it down. So B if you want to find this heat, then you have to use the thermodynamics first law. The thermodynamics first law tells us the change of the internal energy is going to be equal to the work plus the heat. Okay, so the change of internal energy is equal to the work plus the heat. Now, have to be very careful when you do this kind of calculation. The work can be done by gas, and you can also describe the work done by the environment. So in this equation, when you write it in this way, you are looking at the work is done by the environment. That means it's outside of the gas. You do some work from the outside to the gas itself. Then you can write this equation over here. This heat is also from the environment to the gas. And which means it's the outside. And then this will be like similar to this situation where you have a piston, a pipe like this. And piston is right over here. And the heat, it could be like a candle that you light on, and it will give the heat to the gas. So this is from the environment to the gas. Okay, if you look at the work done from the environment to the gas, that means you have a force going from the outside instead of the force coming from the inside. But if you flip the sign, then you can also write this. So if the environment do the work to the gas, if you flip it to the gas do the work to the environment, you simply put a negative sign. Okay, so I can write this in terms of another way. If I wanted to find out what is the work done by the gas to the environment, which is this number that we got from here, then we can find out what is the change of the heat during this process. Now, this change of U is the change of internal energy. This change of U depends on the temperature. If you don't have any of the temperature change, then this will be equal to 0. Why is that? And if you remember how we define the temperature is the kinetic energy in average, translational kinetic energy per particle. If energy of this, if the temperature doesn't change, meaning the energy doesn't change. And that means the internal energy is going to be a constant. So the change of a U will be equal to 0. And because this is equal to 0, that means this energy will be equal to our Q and minus W. This is done by the gas. This is coming out from the environment. And that simply tells you this work is simply equal to your heat from the environment. So to answer this question, it simply means if you wanted to let the gas do the work to the outside and to keep it at the isothermal, that means you have to give the energy from the outside. You have to give the energy such that the gas will do the work to the outside. And that amount of the work and that amount of the energy is the same as the amount of the work done by the gas. So that is equal to 2.7 times 10 to the 3 joule. Okay. You can also expand this by looking at the different processes. So if you look at different processes, such as if we say this one will return to its original volume, like this one here. If we say this is the process, this is the first process that you go through, it's an expansion of the isothermal. What happened if we do another process, which is go in this way, and that will be the second process. And what is the second process called? If you look at the process, you start from the right corner to the left corner, and they keep the pressure to be the constant. So this is also called the isobaric process. So if we extend this, the gas will continue and isobaric. If it go through this isobaric process and return to the original volume, then how much work done by the gas? Well, isobaric, we just show you how the work done by the isobaric. Then it's told is simply just the area. It's simply just this area that you are looking at. So the work done by the gas is going to be equal to the P at the final situation times change of V. Now this change of a V, you have to do a calculation. We know the change of a V is that you start with this one here. This is a 10 liter. This is a 3 liter. So you are looking at final, which is a 3 liter minus 10 liter. And what is the liter related to the meter cube? You have to calculate that because the meter cube is the one that we use to find a joule. You cannot simply use the liter. So 1 liter is equal to 10 to the third centimeter cube, and that 1 centimeter cube is 10 to the negative 9. So this will be 10 to the negative 6 meter cube. Right, 100. Actually, this will be 6. 1 centimeter cube is equal to 10 to the negative 6 meter cube. So if I multiply with 10 to the third, this one should be negative 3. Okay, so we can put this liter in here in the equation, but we still need one more thing. What is the thing that we are missing here? We don't know the pressure at a final situation. But because this is an ideal gas, can we just use the ideal gas law to find out the final pressure? Well, the final pressure is equal to nRT over V final. What is the N? Is 1 mole. The R is 8.312 joule per mole K. And our temperature in this case is 273 K, and over the V sub F, the V final. So the V final is how much? What should be the volume that we use here? Well, this is the one of the thing they have to be careful. We are looking at this point here. We try to find a pressure at the final, and because I know the temperature at here is 273 degrees. If I look at here, the temperature at this point would not be the same because they are not on the isothermal curve. This temperature will be a new temperature. This temperature is different. So if you use this point to calculate the pressure, you have to use the volume of this point as well. So you're using the final position of the volume. And that is the 10 liter. So that is the 10 times 10 to the 3, and well, actually times 10 to the negative 3 and meter cube. And then you can find the P final, that will be about 22.7. You know, it should be larger than this. That will be, actually, I have a number 226590 meter Newton per meter square. That's our pressure, and which is a Pascal. And then you can put this pressure to the equation to find the gas work. And a change of the volume will become 3,000 minus 10,000 times 10 to the negative 6. And that will give you the work. And that work will be negative 1.59 times 10 to the 3 joule. Okay, so I hope that you understand how we derive the work done by the gas in the isothermal process or during the isobaric process. The equation is all the same. It's simply just the work is equal to P times the V, and you do the integration from the VI to the VF. Based on how the pressure change with volume, then you use different way to do the integration and simply represent the area under the curve. So this is the end of this video.